All right, so before we get going too quick, one thing I wanted to mention was I had mentioned registering your iClickers. If you do get the app, I believe if you sign up with your Ball State ID, like there's nothing to register, it will just automatically be able to link up the Canvas using that Ball State ID. They changed it a little bit from kind of how it used to be, so you shouldn't have to register if you're using that iClicker student app on your phone. Yeah, the physical version, though, you will still have to get on and register that on Canvas. And I will expect that you've gotten that by Monday, and we'll start using them for points on Monday, okay? Any other questions for me before we kind of get going into things here today? All right, so I do have this recording here. We will start to work on some Excel stuff later on in the class. Again, we'll start out like we don't know anything about it. But it'll be good to have that recording to kind of use the reference. Let's see. There we go. So we talked about types of data in the sense that we talked about like continuous, discrete, qualitative versus quantitative variables. So what I want to kind of start out with today is types of data sets, right? So one type of data set that we'll see is cross-sectional, and we'll kind of use these quite a bit, especially early on. And it's basically we've just collected some information, right? We have a variable about several subjects. This could be countries, companies, and individuals, but at one point in time. So I think I've got some examples here, right? Maybe I just collect GDP and then education expenditure data for several countries here, but all in the same year, 2011. I've got some other examples here, like even if, let's say at one point in time, we kind of think about, we've collected this data. Oops, that was from my other class, you can ignore that. So we've got 2020, 2010, 2000, 1990, but all this data was collected at the time of the 2020 census. So this is one that looks a little bit different. Don't want to confuse you too much, but the idea of cross-sectional, which might be a better way to think about it, is that you've got one time period, and you collect data on several different subjects. Now you can have several variables, right? I've got GDP as one variable, primary education expenditure is another variable, which they were all collected at one point in time. Time series, I've got outlined here, is going to be when I've collected data on one subject across multiple points in time. So a good example of that, I've got the United States, one subject, right? And I've collected their unemployment rate across all these different years. Okay? I'll eventually here today show you how we can graph this and how useful this time series data can be to tell a very nice, easy, quick story. Panel data is basically like match those two types together. I've now got several subjects across several periods of time for which I'm collecting data. So I had some old ISTEP data from 2009 to 2011. You kind of see here, I'm just showing you three subjects that had however many students that were in Indiana over that time period, where I've got several subjects, several students, and I'm collecting their ISTEP scores from several different time periods or several different years. So those will be kind of the types of data sets that we look at. Like I said, early on, we'll probably primarily look at cross-sectional stuff. If you were to go outside this, like kind of take the advanced stats, you'd start to realize there's some really cool things you can do with panel data, and it's usually a lot more useful. But we won't dive too far into those subjects in this class. So just some more terminology stuff before we kind of jump in to kind of doing some data visualization. So population and sample data, those are other two types of data sets that we'll be thinking about. So population data is like if I wanted to know what the average income in the US was, I went out and collected information from every single person about what their income was. Then I would have population data. I have every single person in the United States in that data set. That's far and few. We don't often aren't able to work with a population data set, right? That's a huge data set. It's hard to collect all that information. We try to do it with the census, but that's only every 10 years, right? And there's a reason why, because it's very expensive. And we'll talk about, it's also just kind of not practical in a lot of situations. So we're left with collecting sample data. All sample data is some small subset of the population. So I might be interested in the average income in the US. I can't go get everyone's income. Maybe I go randomly select 1,000 people, collect their income. That's my sample data. So once I have this sample data, We're going to use that sample data, come up with what we call descriptive statistics. So these are things like the mean or the average. We'll talk about several other statistics we can calculate. And then those statistics from the sample we'll use to make inferences or make assumptions about the population, right? We assume this sample is representative of the population as a whole. So even though we don't have the population data, we can use sample data as kind of a best guess. Right? Now, so that kind of, where did I go? Let me skip ahead here. Right, so that idea is statistical inference, right? Using what we see from the sample data to make inferences about the population. Now, I kind of mentioned, it's too expensive to get population data. Sometimes it's impractical. The example I always give is like, let's say I want to know the average weight in the US. So I go out and I weigh every single individual, right? That is going to take a lot of man hours. It's going to take a long time. By the time I get that data set together, what's probably happened to some of the weights that I recorded. It's going to go up or down, right? So now I've got data that isn't even up to date. So sometimes it's just not practical to go out and to be able to collect all the population data, and so we're stuck with our sample. And that presents some challenges and issues that we'll dive into later on in the course. But for now, we just need to know the difference between the two. Population is every single subject in that whatever group we're interested in. Sample is just a small subset. Don't worry too much. Descriptive statistics, like I said, we'll talk more specifically about the type of statistics we're going to calculate. And then the statistical inference, this idea will pop up throughout the semester that all we have is sample data. We can use that to make inferences about the population. So we'll talk about our first statistic, or the first way we're going to visualize data. So we'll go back, we'll use some qualitative data, which was just some letter grade data. I got rid of the pluses and minuses to make it easier. And I've got 9 people here. So we're going to come up with what we call frequency distribution. It kind of tells us the distribution of a specific variable, in this case, letter grade. And all we're going to do is count the number of times, we see every single possible response. Well, for the letter grade, A, B, C, D, and F are the only 5 responses that we have here. Kind of kept this simple. So we go through and count the number of students who got an A. So we got 1, 2, okay, so the frequency for the response of A is 2. Then we go to the next response, which would be a letter grade of B. 1, 2, 3, 3 students get a B. You write that down. We just go through every single possible response and count the number of observations that had that response. Okay, pretty easy, right? Especially with a small data set. Now, if I got a couple thousand observations, this is not very fun to do by hand, which is why I want to start looking at something like Excel that can do it for us. Doesn't matter if we've got 100 observations or 100,000. It's really going to take us the same amount of time. Right? So I'll give you a little bit of a glimpse into this, I think, before we leave today. But for sure, Monday, we'll start really kind of seeing the power of Excel, I think, in some examples I'll show you. So we've got our frequency distribution. It's nice because I can kind of quickly see, like, yeah, most of the students in this class are getting B's, or kind of, there's a couple A's, a couple C's. Not a whole lot of people are failing, right? And so that frequency distribution gives me a quick kind of snapshot of the data. Now, obviously, with 9 observations, I could kind of see that anyways. But if I had like 1,000, well, then the frequency distribution is going to tell me a lot more, right? Because I can't look at 1,000 observations and like eyeball exactly how many were getting A's and so on and so forth. So this is good. So we got our frequency distribution. Now we might be interested in kind of taking this a little bit further, which is coming up with a relative frequency. So it's great to know that 39 students got A's, but I might be more interested in what proportion of the students got A's, right? If it's 39 out of 50, well, that's pretty good. But if it's 39 out of 500, well, that's not very good, right? So I can convert these frequencies into relative frequencies by simply dividing by the total number of observations, right? So to get that relative frequency, I'm just going to take every category's frequency and divide them all by the total number of observations. So there was 5 A's, and there was 10 students. 5 divided by 10, that relative frequency would be 0.5. Right? So the way that we'll think about these relative frequencies will also kind of be synonymous with the word proportions. Right? The proportion of the students that got an A, 5 out of 10, would be 0.5. Right? So relative frequencies, proportions, really you can use those two terms interchangeably. Right? So what does this look like? So I had that old, I think I showed you last class, that Cubs roster data. I just went back, counted the number of players that were in each one of the positions that were on that 25-man roster. I've now got my frequency distribution. Now, I shouldn't have anything that has multiple, or at least we won't for now in this class deal with anything where you would see, you know, a player have multiple positions. We're assuming that they were assigned just one primary position, right? And so I should have counted every single observation once and only once. So then when I add the frequencies, if every player has been counted one time, my frequency should add up to the total number of observations. Okay? So here I've got 25 as my total number of observations. How do I turn these frequencies into relative frequencies? Just divide each of them by total number of observations, 25, right? So I just divide every single one of these frequencies by 25, and I can construct a nice column of my relative frequencies. I think this is on the slides. If you can see it, I guess you can cheat a little bit. But what should these relative frequencies always add up to? Close, you're thinking a little bit further, but 1, right? Remember, these are proportions, so they're always going to be decimals. What's the highest relative frequency I could ever see? Every student in the class got an A, the relative frequency would be 1, right? All, 100 students, all got A's, 100 divided by 100. The highest relative frequency we could ever see is 1. Generally, we won't see it be that high, right? But if we add them all up, they should always add up to 1 because what's in our numerator here? Well, that's just the frequency. We know the frequencies add up to the total number of observations. So if I add up these numerators, I'll have the total number of observations. They all have the common denominator of the total number of observations. So these should always add up to 1. If you ever calculate your relative frequencies, you add them up and you don't get 1, you know you made a mistake. You hit the wrong button on the calculator or something. Okay. Nothing too crazy yet. We get questions on anything we're up to. So we'll go one step further. Someone kind of jumped the gun already, thinking about what the relative frequencies are up to. Maybe instead of proportions, maybe what we want are percentages, right? So I come up with my percentage frequencies by doing what? Well, the relative frequency is like 5 out of 10 students got A's, so 0.5. What percent should that be? Intuitively, 50%, right? How do I make that conversion? Well, I'm really just moving the decimal point 2 places or multiplying it by 100. So to get my percent frequency, I just take that relative frequency, right, which is represented by this, and multiply it by 100. So nothing too crazy here yet. Really, it would be working with a large data set, just coming up with those frequencies. Once you have those, it's pretty easy to convert those into relative and then 2% relative frequency. All right, so we've got some sample data. This might be something like what an IClear question would look like. I'd show you this and I'd say, okay, look, the percent frequency here for deaths that come from heart disease in 2021 was about 20.6%. How did I come up with that? Well, if I've got all these different causes of death, and I had this catch-all category of others, so that's how I made sure I was counting every single cause of death at least one time. And I grabbed this from the CDC. They like have the death certificate data. They basically just like store all that, and they choose a primary cause of death. Right? So there can be multiple, but they choose the primary, and that's how they identify the cause of death. So we had about 3.4 million deaths in 2021. 696,000 came from heart disease. We come up with the relative frequency. We take the number of deaths that came from heart disease, or their frequency of death, divided by the total number of observations, or the total number of deaths. And then one more step, which would be if I want the percentage, I have to multiply it by 100. Yep. So I would walk you through that, and then I would kind of say, okay, here, solve for X, right? So what percent of deaths are coming now from cancer? And so I just worked through one, or at least explain the steps, and you kind of can see, we had the equation on the previous slide. Hopefully, I give you a minute or so, and you can kind of come up with what the correct answer is here. But a lot of times, I'll give you answers where, especially for in class, I just want you to understand the principles. Like, don't get too lost in the formulas. We'll have a lot of formulas. Some will get pretty complicated. And we do have to plug numbers in and figure out what the answer is, but don't get too lost in the equation to forget what the statistic you're calculating actually tells you. So here, if I want the percent frequency, that's telling me the percentage of deaths that came from whatever cause I'm looking at, in this case, cancer. Well, if I know that there was about 700,000 deaths from heart disease, and that was 20.6%, then the percent that comes from cancer has to be what? Higher or lower than that? Lower, right? Fewer people die from cancer, so the percentage has to be lower. I can rule out A and B right away. In fact, A, I can rule out without knowing anything, because what's the highest percent frequency I could ever see? If all deaths came from cancer, it would be 100%. So right away, I can take a pretty good guess. I can take a more educated guess at this. And I'll set up a pretty good portion of the exams. I'll have multiple choice and short answer. But those multiple choice questions, I actually sometimes think it makes it a little bit easier in the sense that if you know the principles, it can often lead you to be able to rule out one or two of the answers and take a pretty educated guess, even if you have no clue how to enter that formula or how to kind of, if you're having trouble kind of getting things into your calculator. So right away, we can rule out A and D. C here, seems pretty unreasonable, right? If 700,000 people dying from heart disease is about 20.6%, 600,000, I don't think the drop off is going to take us down to 0.18. Now, if I thought maybe I entered in my calculation, like, well, I got 0.18. What did I probably forget to do here? Probably forgot to multiply it by 100, which is then what gives me that 17.8%. So then usually I'll show you, here's the work on a separate slide. It's probably left off the skeleton slides if I'm using it as an actual after the question. But the complete slides would have the problem worked through. So if you wanted to go back, usually I tell people as we get closer to exams, if they're looking for more stuff to study, I say always go back, find the slide that say I could question, make sure you know how to solve it, right? So always make sure I kind of give you kind of the solution there in the complete slides. Any questions on this before you keep moving? I'm going to start doing some data visualization. I'll probably hop over into Excel a little bit. So we can do all kinds of graphs in Excel. So let me see here. So we can do bar charts, we can do pie charts. I mean, you guys probably seen pie charts in like 8th grade science or something, right? Or bar charts. So the general idea of what we're going to do is we could take heart disease, cancer. Basically on our x-axis, we could use these different responses to the variable of causes of death. Then for every single type of response, we could think about, and just because I can remember the numbers easier, we could have our y-axis be the percent relative frequencies. Right? So what percent of death came from heart disease was what, roughly 20.6. I would draw a bar vertically, maybe shade it in, right? To kind of show this is how many deaths came from heart disease. Then cancer, we said it was what, about 17.8%. So I draw a bar up to that point on the y-axis for cancer, so on and so forth. All right. That's basically how, if I want to do it by hand, I would create this vertical bar chart. Now in Excel, it's way easier. So I'll show you here in just a second. We can come through really, really quick. Right? So we took this data and then we wanted to put it into not a percent frequency bar chart, but just a frequency bar chart. So my y-axis would be the frequency or the number of deaths. Looks something like this. Right? So, it's a nice, easy, quick visualization. Obviously, there's a lot of other types of deaths. The reason why we created this catch-all category, though, is if I started listing every other type of death in order, right, this bar chart's going to get really, really long, right? And so a lot of times it makes sense to kind of create one of these catch-all categories if the number of responses I can see, is a really large number, right? If I was doing letter grades or something like that, I don't need it because we're in 5 categories. But, it's nice here. I can kind of see, and it depends on the question or who you're presenting to, but here I can see like, man, 700,000 people a year die from heart disease. If I'm the American Heart Association or something, I don't know if that's an actual organization, but it's something like that, right? And they're trying to, go to politicians and ask for more money from the government. This might be a good thing to show like the absolute number of people that are dying. But maybe I'm trying to like say, well, look, the percent of people dying from this particular cause relative to other causes, I might want to show the percentages, right? So if instead I wanted to graph the percent frequencies, what's going to be true about that graph? There's only going to be one thing that changes. In fact, it's going to look exactly the same. Whoops. So here was the frequency graph. Here's the percent frequency. Nothing changes except what's on my y-axis, right? And the reason why is because if I divide numbers by the same thing or I multiply them by the same thing, it doesn't change the relative size of those numbers. So for instance, 2 is half of 4, right? Agree with me on that? If we divide both of those by 2, and now have 1 and 2, 1 is half of 2. The relative size of those numbers doesn't change. And then it works in reverse order too if you multiply by the same thing. So when we created these percent relative frequencies, we divided everything by the same number, the total number of observations, and we multiplied everything by the same number, 100. So the relative size of our graphs, or our categories on the graph are exactly the same. We could also throw these into a pie chart. It looks something like this, the bigger the slice, the larger the percent. Like I said, you've probably seen these in high school. They're not overly exciting, right? So, but they are a nice, quick way to display this frequency distribution, right? Very quickly, I can see the leading 2 causes of death by far and away are heart disease and cancer. Any questions on this before we jump into Excel? I'll show you how we do these in Excel. I think that's what this actually says, right? So we'll do some qualitative tables in Excel, and then probably won't go to quantitative today. I'll probably just show you just some more general Excel stuff that kind of sets us up for Monday. So I have on Canvas, right, under the Files tab, an in-class data folder. Excuse me. And there's this graphing data week 1 file. So I'm just going to pull that up. I'm going to start talking about it as though you know nothing about Excel. So the file that opens up, we call workbook. I'm not going to quiz you on the names. I'm just, giving you an overview. Within the workbook, we have 3 different worksheets down here. I can add worksheets, right? They start out blank. If I right click, I can rename them. I can delete them. It's really all you'll need to know is if you add them, you can rename them or delete them, probably for the sake of this class. So here we've got 3 different data sets, right? So this first one that we're going to look at, let's go to cause of death data. Okay. So I've got all these graphs created, which is basically the ones that I put up on those slides. But I'm just going to click on each one. I'm just going to delete them for right now so I can show you how I created them. And if I ever forget, remind me to zoom in so you can actually see what I'm doing here in Excel. Okay. So I've got these causes of death, I've got the number, the frequency, and I've got my percent frequencies. Right? So the way that we'll kind of, Excel works, and I'll just tell you this now before I show you the graphing technology, like every single one of these cells we can name, right? So like this cell is C3, right? And this cell is A9, right? So we'll start using what we call cell references, right, to indicate what cell we're looking at. Now we can use these cell references later on. I'll show you a little bit how we can use them to be pretty powerful. But for now, we just know that each cell has a reference name. So what I'm going to want to do is take each one of these causes of death. That's what I want to be on the x-axis. And then I want my y-axis, I could just say, I just want it to be the number of deaths or the frequency. So I'm going to select those 2. So I'm going to select my causes of death and the frequency there just by clicking, left clicking and dragging across them. Okay. And then I'm going to go up to insert. Now it looks like there's 2 types of bar graphs. This one we don't want to use, right? It's called a statistics chart. We'll talk a little bit more about that on Monday. Here we've got our column or our bar graphs, right? We're going to do a vertical one. If you wanted to, you could even make it 3D, right? You could change some stuff. There's a little plus sign here. You could add some axis titles. You could, click here, change the chart title. I'm not going to be as concerned with that stuff. I just want you to be able to take the data and get it into this graph. All the fancy, like you could change colors and add things. I'm not really worried about that, right? That's another class, right? How to make data presentation, right? Or something like that. All I care about is that you can get that original data into the graph, okay? So that's not too bad. I mean, you highlight the data and you inserted a bar graph, right? That doesn't seem too bad. You could do the exact same thing. I'm gonna have to scroll down here and drag this out of the way. Oh, maybe. Except I probably got zoomed in too much. Oh, come on. All right, there we go. So maybe instead I want to create a bar graph using the percent frequencies. And the problem is I can't drag and select those without selecting the frequency column as well. So what I'll do is I'll first select these causes of death, or my y-axis kind of labels. I'm going to hold control, or if I've got a Mac, hold command. So anytime I tell you to do something in Excel and I say control, that means on a Mac, you should be using the command key. Okay? So hold control, or if you're on a Mac, hold command, and then select the percent frequency column over here. Right? So select the names, hold control or command on a Mac, and then select the percentages. Now it's just inserting another column chart, column graph. Okay? Pretty easy. And now the only thing that's changed, the y-axis has percent frequencies instead of the actual frequencies. Any questions? Nothing overly interesting. This is pretty basic, but this is how we can do graphs. So I mean the same thing. If I've got these selected, I could go to insert, select my pie chart, right? And I can create my pie chart as well. Right. So we're going to go over to this unemployment data. I'm going to zoom in on it here. And if I can get the right tab so you can see what I'm doing. And this is just, I've got the unemployment rate for the United States from 1991 all the way to 2021. So how did I just do that real quick? So instead of selecting this with my mouse to try to create a time series graph, there's a little bit of a shortcut you can use to select an entire column of data, right? So what that shortcut is I'll select the name of that variable, hold Control and Shift at the same time, or hold Command and Shift on the Mac at the same time. And as I'm holding those, hit the down arrow. Notice it sends me and selects for me all the way down to the very last observation. Right? Now, if I wanted to select both year unemployment rate while still holding Control and Shift or Command Shift on a Mac, after I hit that down arrow, I can then hit the over arrow. And now notice it's selected both of these variables all the way down to the very last observation. So that's going to be really useful when we're dealing with large data sets where Control Shift, I can select the entire column very quickly, as opposed to, like, especially on a laptop, like trying to scroll with the wheel, I guess becomes an absolute pain, right? So that shortcut's really helpful. Now there is an issue. You wouldn't think this. Everything else we did was pretty easy, but if I go to insert and I want to do a time series graph where it kind of shows how the unemployment rate is changing over time, you might think, well, I've got my X variable selected. I've got my, Y variable selected. Let me just put a line graph in here. But unfortunately, it tries to treat this as two different variables, right? And that's not what I wanted. So I'm going to delete this. And the easier way to do this is to select this variable, and I'm doing it with my mouse. You could use the shortcut if you wanted to. That I want on my y-axis, right? The variable that I want to see, how is the unemployment rate changing over time? Okay. So I'm going to select that unemployment rate, go up to insert, and then select this line graph option. Now that looks a little bit more interesting. Now the problem is I don't know what year this was, right? It just started from 1 and went to the very last observation. So to put these years on the x-axis here, I'm going to select these numbers. So just left click on them. I'm then going to right click, and I should have a select data option. So this will look a little bit different on a Mac, but you still should have like a toolbar, or you should have something that says horizontal axis labels, right? And then right next to it on a Mac, there's like a toolbar kind of like there is up here. So you'll want to select, like click on that toolbar, or if you're on a PC, there's this nice edit button. So I'll hit edit. Now when now I've got my toolbar here. Now I'll just select the years. And once again, if I wanted to, I could Control Shift or Command Shift, hit the down arrow, and it actually selects all those years for me. And you don't really have to worry about what it's doing here yet. But by selecting those years, it's telling Excel, hey, take these years and use these as my x-axis labels. Okay. So now if I hit OK and I hit OK and I go back to my, whoops, what did I do wrong here? I think I accidentally hit a button here. So go edit these again. We'll delete this. Select the years again. Now make sure I don't hit a button on the way out. There we go. Now it's got all my years in there. Right? So that's probably the easier way to do it. Like I said, if you try to select it all at once and then insert a time series graph, it treats it as two separate variables and tries to throw them on the same graph. When in reality, all you wanted those years to be was your labels on the x-axis. Okay. Any questions on that? So let me see here if I can get this all to be on this. There we go. So the reason why we like time series graphs is, right, I can now tell a pretty quick and easy story just by looking at this graph. I don't have to see the original data, right? I've got, you know, unemployment was pretty high at the beginning of the 1990s. It fell throughout the entire decade, you know, remained fairly stable in the early 2000s until we had the Great Recession. We saw a spike in 2009-ish. It then fell for the next decade until we got COVID, and then it spiked again, right? So I can, you know, if I don't know what happened here, like I'm like, why in the world did this spike? And then do some Google searching. Oh, there was this thing called COVID-19 in 2020, and it caused, you know, unemployment rate to skyrocket, right? Or we had the mortgage kind of crisis that kind of caused it to skyrocket in 2009. But it gives me a quick shot where, like, I should look at this and say, well, something clearly happened here, and something looks like it probably happened here. Maybe I should go investigate that a little further. Right? What might even be better is if well, I'll show you this hypothetical. I'm going to make these numbers up, so bear with me. So maybe I've got the US unemployment rate. Maybe I want to compare that to Canada. So I'm just going to make up some numbers here. You can kind of imagine. I'm just going to use 2.7 for the remaining, so I don't have to make up all of those. But I at least give you the idea that even if I didn't just want the US unemployment rate, let's say I wanted to create a time series graph, but I want to have the unemployment rate of several countries. Right? So I've got the US unemployment rate and Canadian unemployment rate. I basically go through the same process, right? So I'm going to hold Control and Shift, hit the over and the down arrow to select both of those countries' unemployment rates. Now, when I go to insert that line graph, I've got US unemployment rate is blue, Canadian unemployment rate is orange. I'd have to go back in and change the years again. But I can kind of see, like, over time, what was the differences between the two countries, like, movement in their unemployment rate. Now here's this made up data, but like if we have the actual data, we can make some comparisons then, just looking at those lines. Okay. Any questions over that? So we don't have to do them on separate graphs. We can put them all in one. Yeah.
Was your US data, was that accurate?
Yeah, I actually went and grabbed that from the Bureau of Labor Statistics. So that's why it actually does kind of make sense. You know, we saw a spike in 2009, we saw the spike from COVID. In the 90s, it was actually pretty good time for the US, right? Where we saw unemployment rate fall the entire decade. So any other questions? All right. So let's go to the last worksheet, scatter plot data. Okay. So up to this point, we've kind of been looking at one variable or one variable for different countries, right? The unemployment rate for the US and Canada. But I might be interested in kind of what's the relationship between two variables, call it variable X and variable Y. Right? So I think on the slides, did I not? Where is it? Here we go. I'm jumping around a little bit. But we're going to use what we call a scatter plot. So I've got two variables, X and Y. I'm going to basically every observation, I'm going to have recorded two things. So I use this life expectancy data. So I've got healthcare expenditures per capita and life expectancy for all these different countries. I might want to know, okay, if the average healthcare expenditure is higher in a country, does that lead to higher life expectancies? So I'm going to graph these two by putting healthcare expenditures on my x-axis and life expectancy on my y-axis. Right? After I do that, I can kind of see every single country is basically going to be 1 point on this scatter plot, right? So I've got every single country here. I just pointed out a few of them just to make, I don't know, just so you kind of line it up with the original data. But we can see once I graph this as a scatter plot, you know, if I try to draw a line that best fit this data, I don't know. Maybe you could argue it's slightly positive, but it kind of looks like here it's just all over the place, right? It doesn't look like healthcare expenditures are going to be that good at predicting life expectancy. Like I said, maybe a slight kind of positive best fit line here. But it is kind of interesting to see, like, the US really screws with this, right? We spend the most on our healthcare, but our life expectancy is lower than like every other major country, well, with the exception of Poland. I don't know if they count as a major country, but all right. But you can kind of see here, they're spending the least and they have the lowest life expectancy. So it's kind of interesting to identify outliers with a scatter plot, but usually it'll show you a more kind of consistent story, or a consistent relationship between two variables, X and Y. So I think here, yeah, I've got this percent vaccinated and the number of new cases. I don't know. I just don't care about COVID as much as I don't know, I used to. I used to think it was kind of interesting to see, like, there's not a real strong relationship here either. I believe this was by state, so each dot represents a state. You know, the percent of the state that was vaccinated and the number of new cases that they had. I think this was last spring or last fall. Really not a strong relationship. So how do we create these scatter plots, right? So I've got my scatter plot data here. I try to think of something that might have a relationship. I actually haven't created this scatter plot yet, so I'll be just as surprised as you guys are of what comes out of it, right? So I had violent crime rates and students who were not reading proficiently, right? So here, higher numbers are bad, right? You know, we could kind of look through this. I thought there was an 80 in here somewhere. Oh, here's DC, right? Washington, D.C., 77% of their students did not register as reading proficient. And I forget the exact metric that they used, but it gives us some idea. So what I'm going to do is select both these variables. I'm going to use the shortcut because I hate scrolling on my laptop. So I'm going to select the violent crime rate, hold Control and Shift, hit the over arrow, hit the down arrow, selected the entire column of data for me. And then I'm going to go to Insert. And then down here, I've got this scatter plot option. Now I can kind of see, okay, here's my crime rate. And then up here is kind of the percent of students who are not reading proficiently. Well, this, you know, if I had to draw a line that kind of best fit this data, I would argue it's pretty clear to see that it's kind of like this positive relationship, right? As the percent of students that aren't reading efficiently goes up, crime rates also tend to be going up, right? Not overly surprised by that, right? It probably, you know, students not reading proficient is likely correlated with probably dropout rates, and then those are always significantly correlated with kind of crime rates here, right? So what's one easy fix? I mean, one way we can maybe help with some of the crime rates, go back into early education and try to make sure that we're improving reading efficiently early on in a student's life. You know, there's this, obviously, it's a much more complicated issue. This is somewhat simplifying, but it's a nice, quick first glance look at it, right? It says, look, something's going on here, right? There's definitely some type of correlation here, okay? Any questions on that? And you can play around with, so if there's this plus sign, you can play around with data labels, like putting the actual numbers on there. You could add axis titles to it to make it a little bit more clear of a graph. But that's the general idea of how you would create a scatter plot. Okay. Any other questions on that before we keep moving? So the next couple things I'll show you are just some useful things to know about Excel, right? And that will help us once we get to the next thing, which is, well, what if I want to create bar graphs, but not for qualitative variables that have a limited number of responses, but like, let's say I want to create a bar graph for income in the US. Well, what am I going to do? Count the frequency of the number of people who make $0, put a bar there. Number of people who make 1 cent, put a bar there. Number of people who make 2, all the way up to, you know, whatever Bezos or whatever is making. No, that's ridiculous, right? The bar graph would be the length of the campus, right? So what we're going to do is instead we're going to count the number of people who make, say, between 0 and 10,000. 10 and 20,000, right? We're going to create these kind of ranges of values when it comes to continuous data. So we'll probably get started on that a little bit today, but we'll really tackle that on Monday, right? But it's going to be the same sort of idea. It's just a little bit harder to come up with the frequencies. Once we have the frequencies, creating the bar graphs is just like what we were doing earlier, right? It's just a matter of getting the frequencies from a larger data set. Before we do that, I want to show you a few more things in Excel that'll make that discussion a little bit easier. All right, so these might be good things to write down because we'll probably be using some of these shortcuts or using these ideas as we use Excel throughout the rest of the semester. So I said before I show you that. So one thing that I try to do with a lot of these data sets, it makes it a lot easier just to look at them. So I'm going to select this entire data set by just Control Shift or Command Shift on Mac, hit the over, hit the down arrow, right? Selected all the data here, the states, as well as their crime rates and proficiency, reading proficiency failures. I'm then going to go to this data tab, and there's this option that says filter. It's already selected, but if it wasn't, right, and then I select it, notice it puts these little arrows down here. Now, the reason why that's nice is because if I look here, I've got some options now. First, it shows me all the responses that I could, all of the recorded responses across these different states. But it also gives me this option to sort the data from smallest to largest or largest to smallest, right? And when I sort the data, what it does is it doesn't just sort this variable, it's going to move the entire observation down as well. So it's not like, things aren't going to get mixed up, right? You're going to keep Alabama's violent crime and proficiency rates on the same row, right? So we're just moving the observations. So I'll go largest or smallest to largest. I can see that kind of the states that I would expect, the New England kind of states that have pretty low populations and higher incomes, their students are doing great, right? When I say great, it is kind of sad that whatever metric this was, the best states still had like 50% of kids not meeting it. But my wife's a principal, and I know from experience, like even in good school districts, that's about what it is. So yeah, I don't know what that says about our education system. But anyways, that's a different, I'm going on a side. So if you also scroll down, I'm going to get rid of the scatter plot just for right now. You can kind of see New Mexico and Mississippi have the highest kind of, percent of students who aren't reading proficient, followed by Louisiana and DC. Once again, I wouldn't be overly surprised by this. I'm guessing Indiana falls somewhere in the middle. I should probably doing better than I thought. So I don't know, kind of interesting. But by sorting it, right, you can kind of see pretty quickly like what the highest, what the largest is. You can sort multiple variables, right? So maybe I want to see who has the lowest crime rates, right? I could sort that the other way. Who has the highest crime rates? DC wins that one by a long shot. Alaska's screwed up because they don't have any people. And so like one violent crime has a huge kind of increase on that variable. But kind of interesting to play around with that filter tool, right? And that'll kind of help us out at later points in the semester as well. So that's kind of a nice thing. I always try to download the data with that. If I've got several variables kind of in these early ones where I only had like one variable, I didn't even bother filtering it. But whenever I've got several variables, I usually try to kind of upload the Excel file so the filter's already turned on. But if it's not, the way you do it is just highlight the data and then hit that filter option under the data tab. Okay. So another thing that we can do in Excel is if I put an equal sign, this lets Excel know I want you to do math or use a built-in function, right? And so maybe I wanted to just take, 2 divided by 10, and I just want Excel to give me that answer. So I can basically use Excel to be a calculator, right? What's 8 plus, 234? And I'll spit that answer out. Right? So I can do math or use Excel to be my calculator here. But I can also have it put the value that exists in another cell already. So let's say here, I want to put cell B2's value into this cell. Well, I could type in 999.8, but then, maybe I want to look at newer data or the violent crime rate data comes out and they've adjusted it and that value changes now. Well, then on every time I'm using 999.8, I've got to go in and change it in every single place where I used it, right? So instead of typing the number in, I can use this equal sign, click on the cell, right? I want 999.8 to eventually be in this cell. I'm just selecting that value. Excuse me. And it automatically puts in this cell reference, right? So that equal sign says, go to cell B2. So go to cell B2, grab whatever values in that cell and put it here, right? So if I hit enter, sure enough, that 999.8 shows up in that cell. Now, why is this useful? Well, when we start working on some things and we're gonna see how using cell references and copying can make our life really easy, where instead of having to enter something in like 20 times, we only have to enter it in once and then copy it down. It's a little bit of foreshadowing. It's probably not quite clear yet, but we are able to use those cell references to be more powerful down the road. Yeah.
So
All I did, yep, maybe I want this cell, right? If I click on that cell, it automatically, now I can type it in too, but for me, it's usually a little bit easier just to click on the mouse. Yep, and then we'll hit enter. Now in this cell, it put what's in C8. But why this is useful is now let's say, some report comes out, where I grabbed the violent crime rate was, I think it was on, I know it comes from the CDC, but it actually was up on the Bureau of Labor Statistics website. So let's say they always do this, like they put out preliminary values and then like 6 months later, they're like, we've updated them, right? Okay, well, District of Columbia was wrong. Maybe it was only 950.4. Well, if I go back to that original cell and I change that value, every time that I use that cell reference for B2, once I change this, it automatically will update all of those, right? So that saves me a lot of time. So some of you accounting majors, like I don't even remember all this now, so the terminology may be way bad. But like if you've got balance sheets and income statements and all these different statements or whatever that you're looking at, you're going to have values where from the income sheet, you want to grab some values and put on the, whatever else you're looking at, right? And so you might have referenced an original starting value several times, right? You'll see this with like loan amortization, like what's your projected loan payment going to be? Well, you can come up with a calculator and do that, right? You can type in all the numbers, what the current interest rate is, the principal amount in the loan, or you could reference certain cells where you put the interest rate. And then if something changes, you don't have to go change the interest rate every single place where you typed it in. You only have to go to that first cell and change it. Now all your cell references will automatically update to that new value. So it saves you a lot of time if things kind of change down the road. Like I said, you can create like some pretty cool little like loan amortization things on Excel by doing that, by using cell references. And as we progress through some examples, I think you'll see why cell references are pretty useful.
So in order for it to change, you have to go in and click on it and just hit some buttons, right?
Yeah. So for instance, what if this became 567? Now it won't change because I'm still like currently in the cell, but as soon as I leave the cell, which probably the easiest way to do that is just hit enter. Notice every time I use that cell reference change, like even if I used it, excuse me, down here, now they both changed, right? So it really becomes really useful when I'm using that original starting value in several other points. Any other questions on that before we keep moving? Okay. So I'm going to go over one more cell here. And let's just say I want to put what's in cell C2 here. Okay. One nice thing, sometimes it's nice, sometimes it goes against what we want to do. But if I left click, so notice when I've used that cell reference, it kind of hides it behind the scene. And then when I hit enter, it just shows me the number. But if I click on this cell and see how this becomes like a thick black plus sign down here in the bottom right corner, if I left click that and I drag it down, that's basically going to copy what's in that cell. Now, the problem is if I typed in the number 77, when I copy that down, it just copies the number 77. However, in this cell, what's actually stored in the cell behind the scenes is this cell reference. So when I copy this down, unfortunately, it doesn't just copy equal sign C2. However many rows I copy it down, it updates the row reference. So instead of C2, when I copy this down one, notice it puts what's in cell C3. Right? So when I'm using this drag option and I've got a formula in the cell that I'm dragging, it'll update those cell references by however many rows I move it down or copy it down. And it also will update my column reference. So let's say I want to go over one this way. Well, now I'm going back a column, right? So instead of C2, it's going to actually put in what's in cell. Oops. B2, right? So however I move or however I copy that, dragging it over or down, it updates it that many rows or updates the cell reference that many columns. Does that make sense? And sometimes that's useful. Like I said, on Monday for sure, we'll have an example where we see how this can be useful. Sometimes it's not, right? So if it's not, so let's say I copy this down. And let's say, no, I actually just wanted the number 77 here, right? I wanted to take whatever this original value was in cell C2, and I want to put that in every cell in this column. I don't know why I want to do that, but let's just say I did, right? We're going to do something that we call freezing cells, right? So freezing cell references just means that when I drag it down, copying it by dragging it down, it won't change that cell reference of C2. So how can I do that? I put $signs in front of the column and the row reference. So $sign in front of the letter, $sign in front of the number. Now if I hit enter, and now if I copy this down, that cell reference stays the same. Doesn't matter that I'm copying it down rows or copying it over columns. It kind of stays the same if I use those $signs. Okay. Yeah.
So I don't need to do anything special, like special settings or anything for the previous thing. You can show us where it would change like B2 or B2.
Nope, that's just like default. All you can actually do is turn it off. And the way that you turn it off is by putting those $signs, right? And there's a pretty nice shortcut. So instead of like having to type it in, let's go back here. So it'd be a good shortcut to know as we kind of get down the road. So let's say I had cell C2 there, and I want to freeze that reference. I'm going to highlight the reference. And if you have a PC, so on some laptops, there's like a function or an FN key if they're too small. You'll hold your function key and whatever is your F4 key. If you don't have a function key, you just have to hit F4. Like on my desktop in my office, I just have to hit F4. And if I do that, it automatically throws those $signs up there for me. Now, when I only have one cell reference, that doesn't save me a lot of time. But if I have a cell that has like 4 or 5 cell references that I want to freeze, that does save me quite a bit of like typing and kind of moving around. Right? Now, if you're on a Mac, what you do to get those $signs up there would be Command T. Right? So not even close to F4, but you'll highlight the cell reference and Command T on a Mac. Okay. Any questions on anything that we've kind of covered here so far? Let me think if there's anything else I want to show you here in Excel before we go back. We talked about cell references, freezing them. We should be pretty good. I know we're not going to have time, I think, if I start. Let me see. Did I have the... Yeah, I got histograms up here, which is what we're going to have to do. So we'll start the idea, and then I will finish up Excel on Monday. So taking a step back now, right? We're done with Excel for now. I might want to create these bar graphs, I said, for continuous or discrete data, right? Now, we'll kind of focus on discrete data first. That's going to be pretty easy, right? Because instead of causes of death here, if I had like, what percent frequency of the households had 0 kids, 1 kid, 2 kids, well, it's just gonna be the same thing. I'm gonna go through the data set, count the number of households with 0 kids, write that frequency down, go through the data, count the number of households with 1 child, write that frequency down. Once I have my frequency distribution, I can turn those into relative frequencies and percent relative frequencies. So with discrete data, it really looks no different than what we're doing with qualitative data. It's just that instead of counting the number of times I see the response of heart disease, I'm counting the number of times I see the response of 0 kids. Well, with continuous data, I already mentioned the issue. Like if we want to look at income, there's just gonna be too many responses. So I'm gonna have to create these things that we call bins or classes, right? And so the idea would be the first bin, how many people make between $0 and $10,000? Second bin, how many people make more than 10,000 up to $20,000? I go through the observations, count the number of people who had income between 10 and 20. Once I have that frequency, write that number down. But once I have the frequencies for each one of these bins, well, then it just becomes exactly like what we were doing before in Excel, right? I just use my frequencies to create my bar graph. So the work in Excel will be a little bit more difficult to come up with those frequencies. But we'll kind of tackle that on Monday. So we'll talk a little bit more about the bins and classes though, to make sure that once we start working with the data, we've got our bins correct. So a histogram is just a fancy word for a bar graph of continuous data, right? It just identifies that I'm showing you the data in a condensed version, right? Because I'm counting the number of responses within a certain range, right? So I've kind of condensed the data down into these different bins or these different classes. Those two words are synonymic, interchangeable. I'll often just call them bins, right? But you might see them called classes. So number of bins or classes, generally we don't want it to be too many. Otherwise the graph becomes way too long. We don't want to have too few. Otherwise the graph isn't very interesting, right? If I say, you know, I have 2 bins, how many people make between $0 and $100,000 and how many people make more than 100,000? It's not a very interesting graph, right? It doesn't really show me the nice income distribution in the US. So there's no set rule. If it comes to a homework, I'll tell you what the number of bins are, right? Or a question, I would kind of tell you the number of bins. And then the way that we kind of, at least in practice, the formula that gives us what the bin length should be, or at least a good starting point, would be to take your maximum value and subtract the minimum value C for that variable in your data set. So I would take the highest person's income, subtract the lowest person's income, and then divide it by the number of bins that I want. So let's say I wanted 6 different bins, right? I would take Jeff Bezos's income, subtract probably the lowest income would be 0, and then divide it by that number of bins, which is 6. Now, it's not always great, right? So we can kind of play around with this, but that's our starting point. Yeah.
What did you say you're calling a bin?
So these bins are going to be this range that we're going to count the number of observations that were in this range. So how many people made between $10,000 and $20,000? And that's kind of that'll be one of my bins, 10 to 20,000. You know, just a couple of guidelines, right? So that's a good starting point, is to use that formula. But we need to make sure that every single one of these bins is separate, right? So I can't say count the number of people between 0 and 10 who make between $0 and $10,000, and then count the number of people who make between 5 and 15, because those bins overlap. Now I could have someone making $8,000 a year and they'd be counted in 2 bins. I have to have the bins constructed so that it's only possible to be counted in one of those bins. So there's no overlap, right? That's all mutually exclusive means, is that there's no overlap of our bins. They need to be exhaustive and that I'm counting every single observation at least once. So a good example I like to use income is because let's say I said how many people make between 0 and 50, 50 and 100,000, 100, 150, 150 and 200, 200, 250, and I stop. Well, there's people that are like making ridiculous amounts of money, over $200,000, who aren't going to be then counted in any bin, right? So what we'll often do to avoid not counting some extremely high or extremely low observations is I'll kind of do that like $50,000 increments for my bins with income, but then I'll create a catch-all category, kind of like I did for the cause of death. Whereas did they make over $250,000, right? So usually we'll kind of construct these bins to be a reasonable length and then create a catch-all category for a situation like dealing with income data.
So for the maximum value, would
Yep.
it be like the largest amount of income?
Yep.
minus okay.
And on Monday, when we go back into Excel, I'll show you pretty easy functions, but we'll start dealing with some Excel functions to identify the maximum and the minimum value, even from a really large data set. Cool. Yeah, just be like I said, the person who made the most had the highest income in your data, the person who had the lowest income in your data set. Cool. And then generally want to keep these bins or these classes the same length. So like I said, with the income, you know, if I'm keeping it 0 to 50, 50 to 100, 100 to 150, I want those bins to kind of be the same range or the same length. Now, to make sure that they're mutually exclusive, I would need to be careful when I'm creating these bins. I'm being a little bit sloppy in my language, because let's say I created the bins where it was how many people make between 0 and 50,000, how many people make between 50 and 100, so on and so forth. What's the problem by doing that? What if I make $50,000? I'd be counting both. So I have to make sure that the equality sign is only on one of those bins. So maybe I say, how many people make between 0 up to and including 50,000? And then the next bin is, how many people make greater than 50,000 up to and including 100,000, right? That way, the equality there, the value of 50,000 would only be counted as one of those bins. And like I said, when we work the Excel example, I'll bring that up again, kind of like really hammer that point home. But the whole reason is because we want to make sure that every observation gets counted once, but only in one of these bins. All right, so just kind of a quick and easy example. And like I said, we'll do this in Excel on Monday as well. But, let's say I have the SAT scores of a bunch of different Indiana high schools, 366. The number of bins I want is 9. The lowest average SAT score is 352. The highest average SAT score is 648. What should my kind of starting point for my bin length be? Or what should the, we call this like the optimal bin length be? Well, I've got my maximum value, got my minimum value. I'll just take the difference between the two. And then I would divide that by number of bins, which we said was 9, right? So there we go. I'll take my maximum value, subtract the minimum value, divide by the number of bins. My bin length should all be about 32.88 repeated. Well, this is where it becomes like, let's think a little bit. If I want to put this on a graph, the starting and stopping points for my bins are going to start to have all these decimals. It's not going to look very nice, right? And so generally we want to use integers. Now the problem is if I have a decimal, this formula gives me kind of a decimal response. If I round down, then my bin lengths, once I kind of build each one of my 9 bins, it won't actually be as high as the maximum value. Okay? So if I use this formula to come up with what my optimal bin lengths are, and it's a decimal, I always need to push it up to the next integer. So even if this was 32.1, I should be using kind of 33. I would still push it up to that 33 for my bin lengths. And I'm not going to try to trick you on this. This is kind of a starting point. On the actual Excel homework, I'm going to actually give you what the bin should start and stop at, so you shouldn't have to worry about that. But when I work through the example in class, I'll show you how we can use this formula and why sometimes it's helpful, but then sometimes it's like, well, I just need to use my brain and come up with some bins that make sense in the context of this example. But this is kind of a good starting point. Okay? I'm going to skip ahead here, because we're going to do all of this histogram stuff in Excel on Monday. But I want to give you the idea, leave you with one more thing, okay? So, once I come up with these histograms, right? I count the number of people who make between 0 and 50,000, 50 and 100. I'm now just going to have frequencies. I could just create these bar charts, just like I did before, right? So once we have these bar charts, they're showing us the distribution of a variable. Well, every variable will have certain distributional shapes. Now, sometimes we won't be able to give it a name, but sometimes they'll fit one of these kind of nice categories, right? So the first one is normal, right? Especially after the first exam, we'll be dealing with normal distributions a lot. So if I graph the data, I think I was using that SAT score data that I was just showing you the example of here. So the different average SAT scores in Indiana high schools. Kind of notice if I were to draw a line through like the top of every bar, with the exception of this little dip here, it's pretty much looks kind of like a bell curve, or what we call a bell curve, right? It's kind of this nice like hill-looking graph, or like a bell, right? And so this pops up a lot in nature, like anything, any biometric, like human height, human weight, have some, I'll show you eventually in the semester, like just like some data they collected on CrossFit performance, and it like followed a normal distribution. Anytime we look at like anything that's a result of biology, we often see a normal distribution. Okay? This is what it looks like, right? Kind of like this bell, where the majority of our observations, the majority of our SAT scores we're kind of in the upper 400s, lower 500s, right? Represented by that's where the highest bars were. There weren't very many schools that had SAT scores that were as low as the 300s or as high as the 600s, right? Those are where our lowest bars are. So it's kind of like the bulk of our data is here. And then as we move in either direction away from that middle point, kind of the frequencies fall off of seeing those really high or those really low responses. We looked at something like income distribution. So they have like a lot of categories here. They actually looks like they broke this down by $5,000 increments, right? So 0 to 4,999, 5,000 to 9,999, so on and so forth. You can kind of see here, and this is some older data, 2010, but the majority of Americans, right, the highest bars are down here in like the $20,000 and even $30,000, right? So, you know, when we talk about averages, right, we'll eventually get there. It's going to be related to kind of these distributions. Right? Well, you can see here the majority, or the highest frequencies are people making kind of $20,000 to $30,000, and it kind of trails off as we look at higher and higher amounts of income. Now I created some catch-all categories here: 200 to 250,000, and then 250,000 over. That's why we get kind of higher bars there. If I was to keep doing $5,000 increments, we would just end up with a really, really long kind of tail getting closer and closer to zero, right? And then stopping at whatever Bezos or Musk or whoever's the richest one. So we would call this, right? It's got a long right tail, a right skewed distribution. Despite the majority of people being here on the left side, we call it right skewed because it's got this long right tail, right? There's actually a more technical reason why, but that's kind of the next topic that we'll cover next week, right? But for now, you have your distribution, like you graph the kind of histogram and it has this long right tail. You would say the data is right skewed, right? We've got some really extremely large values there on the right-hand side, extremely high income. If we had something that looked like this, we would say it's left skewed, right? It's got a longer left tail, right? Good example of this would be like the length of a pregnancy or gestation, right? We see premature births from, you know, even as early as 5, 6, 7 months. We don't see many babies being born at like 10 or 11 months, right? It's not often that we have much of a right tail there at all, right? So we've got left, right skewed, and then the more interesting one here is if we looked at weight, right? So body mass. It looks like we've almost got two normal distributions, right? If I was to kind of draw a line of best fit on the top of these bars. So why on something like, we'll call this bimodal, right? Bi meaning two, right? So what's going on with something like this? I'm looking at weight. Why might it look like I have two normal distributions?
Male and female audience.
Yeah, right. If I separated this out by male and female, here's my male distribution, here's my female distribution. Once we start talking about means, we can talk about how those relate to the kind of look of a distribution here. But if I ever see something that looks bimodal, it probably means there's a characteristic of the observation that is influencing the variable I'm interested in, right? So maybe even if I looked at, I don't know, something like frequency of eating certain types of food, and then if I separate it out by area of the country, maybe it looks like I've got kind of like normalist, right? It's that there's this outside factor that kind of is creating two groups within my data set where I might see just kind of a difference in their averages, right? They both still follow a normal distribution. It's just that one of them is going to have a higher average than the other, right? That's what's happening here. Male weight has a higher average, but it still looks pretty normally distributed. Female weight, lower average, still looks pretty normally distributed. When we graph them together, we get into this kind of two-hill looking bimodal distribution. We'll talk about ways we can with data like that, the more technical way of how we name these left and right skewed, and look at how we do histograms in Excel on Monday. Okay. So before we start class Monday, I want you to make sure you have a physical copy or physical version of the iComputer, you get that registered. I'll start using those in class on Monday for points. Also try to get on and get registered for that next assignment. It's out there. You can probably start tackling a couple of the early questions related to frequency distributions and then calculating relative frequency distribution, although some of it we still will cover next week. Okay. Any questions for you guys out? All right, hope you have a good first week of classes. Enjoy the weekend, be safe, and I will see you on Monday.